Think about how we learn. If you're watching a pendulum to learn physics, but someone keeps bumping the table, you don't try to memorize every single wobble caused by the bumps. Instead, you ignore them to find the real law of motion. In deep learning, we pretty much force models to memorize everything, including the table bumps or noise. This paper introduces a picky way to train. It identifies which moments are just random noise or weird flukes and tells the model to look the other way. On the left, we see the raw data. The red line is the truth and the blue is our guess. Those wild spikes, those are moments the model shouldn't try to fit. They are accidents that do not generalize. Selective learning masks them out. On the right, the error curve shows the result. Without this trick, the model starts memorizing the noise and the test error climbs minus. Yay for overfitting. With it, the error stays low and steady. We are finding the actual signal. Entropy is a technical term with a mathematical definition and a proper theory to go with it, but in our context, a useful way is to think of it as a measure of how many different stories the model is telling. If we look at the same moment from 5 different starting points and the model gives us 5 totally different answers, it's just guessing. Think Rashomon or Hoodwink, but for machine learning, it's really difficult to learn the truth from that. So we calculate the shakiness of these guesses. If the whole thing is too shaky, we don't let those points change the model decision. We ignore the gossip to find the facts. How do we tell a fluke from something we just haven't learned yet? A fluke is like a broken sensor. You'll never predict it, but a new pattern is something you could learn. We use a simple model to find the floor, the lowest possible error for a point. If the gap between our main model and that floor is tiny, but the error is still huge, it's a fluke. It has reached its physical limit. We throw those out so the model doesn't try to memorize a one-time accident that is extremely unlikely to happen again. Now, let's look at what happens when we change how much data we throw away. One might think masking 30 PCT of your data, or even 90 in some cases, would be a disaster. But for jumpy data like exchange rates, the error actually drops as we mask more. It's like clearing static on a radio until only the clear voice remains. For steady data like the weather, you don't need to mask much. The secret is finding the balance where you ignore the junk but keep the signal. It's about being a picky student, not just a fast one. The key takeaway here is that more data isn't always the answer. If your data is full of BS, whatever the source, you're just teaching your model how to be wrong. Selective learning is a simple, universal way to make models more reliable without making them more complicated. By ignoring the parts of the data that don't make sense, the model actually learns the underlying rules of the system much better. It's a smarter way to train that works across almost any model you're already using.